Hello explorers and welcome to another video. Today we are going to talk about hyphenation. I'm excited to tell you that I partnered up with Code Combat to bring your kid a learning opportunity. Back in my day, there were no one that could tutor me, I knew more than the teachers, and I had to put in the work because there were no other option. Unlock your child's coding potential with Code Combat's live online classes. The classes are led by experts who make learning an exciting and rewarding experience. With their help, your child will work through coding challenges and feel proud of their accomplishments. Personal attention and a structured curriculum will help your child become a confident coder. I always said that I hope that you learned something today, and now your kid can. Follow the link in the description and enter the promo code EXPLORER10 at checkout for a 10% discount, and all subscriptions have a 30-day money-back guarantee. And hyphenation might be something that you're not really thinking about. It's just something that works in your word processor and not really a subject that is coming up that often. But I had the problem here that we have some text flowing format and it's hyphenated in order to make it look good. You can't have how much characters on each line and so on. So you need to break it up in some way. And hyphenation is a pretty hard topic. I actually found a research paper by Frank Liang where he discussed the difficulties of actually doing good hyphenation. In the beginning, when newspapers come out, they had some really horrible hyphenations. So if you stop a word at the wrong place, you can actually get a very different meaning of the flow in the text and so on. So he came up with some pretty good rules that could handle most test cases. The problematic thing is there that some words can be hyphenated differently depending on if it's something that a person is doing or if it's something that describing an object or if it's just a name of an object. Then they can be hyphenated differently. So we had some examples of that as well. But there is a bunch of these kind of rules that people have come up with that could work in hyphenation sense. But they are pretty much depending on which character flow that you get in your text. So in order to package this in a good way, because there is people that have created these kind of lists where you can hyphenate things. So there is an English list with 140,000 words that are correctly hyphenated. So Donald Knuth made a research paper about the text format, and in his appendix H for hyphenation, he actually have brought up this issue and have a way of packaging these in a much more dense format to figure out how to actually hyphenate things. And I have taken that dense format, make it even denser, and then made an algorithm to hyphenate things because I thought that this subject was interesting to go on with. So if we switch over to my screen here, we can start with looking at this format that Donald Knuth have. So here we have patents from 9, and there are copyright Gerald Kunish, and they are available to use for hyphenation tasks in normal use. So here we have patterns, and these patterns are pretty interesting. They are actually a way of describing if these three characters come. Let's see here if I can find one example of multiple numbers. So here we have a one that have multiple numbers. It starts with a 5 i.e. 5 GA. And I can say that you can put in a hyphenation before IE, and you can put in a hyphenation before GA in this case. So the format actually works like this. You have a bunch of rules that have characters. You say that the number in the sequence could either be you may hyphenate or you may not hyphenate. And depending on if the number is either odd or even, you may hyphenate. So if it's odd, you may hyphenate. If it's even, you may not. And the number can be from 0 to 9. Every character here has a 0 before it. So if we have 2, EI, 4, this could be written as 0 here. So you have a 0 here, so you may not hyphenate between those because there is a 0 there. So why do we have numbers from 0 to 9? That is because some of these cases are more prevalent and could be better for the hyphenation task. So if you have one that says you may hyphenate a number 1, and then you find the same spot but with a number 2 instead that says you may not hyphenate, then the 2 is higher than 1, so that is the value that you should go for. So it figures out where you can hyphenate or not, and the maximum number in that spot determines if you may hyphenate. And you also see here that we have dots here. Either the dot could be in the start of the word or at the end. And that means that this sequence is only allowed at the start or end of the word. So if we have a word that ends in ER and have an I before, then we may hyphenate between the I and ER. So that is the case for that specific rule. But this format has two different cases. We have these patterns that we need to go for. So those patterns we have here, it's a pattern index here. But at the bottom, we also have these special hyphenation rules. And these are words where they haven't created any rules for them. These are exceptions, an exception list. So associate can only be hyphenated between as and so, and between so and C8. So these are exceptions to the patterns above. And what I wanted to do is create something that could take these exceptions and put them into patterns, so I can just have a list of patterns. That would be nice. So I created this little script here, which takes this text file in and creates a dictionary out. And it also adds some extra values here. First off, I want to say that this is a UTF-8 output. So this should be read as UTF-8 characters. That should give us most of the alphabets. And then we have a left hyphen min 2, which means that I don't want the first character, between the first and second character, to be hyphenated. I want at least 2 characters before I do an hyphenation. And the same goes for the end of the word. The right hyphen min is 2, so you might not hyphenate at the end. And then I go through here and see if I can find the exceptions. So first I remove all lines that has these ending brackets, because I don't need those if I only have patterns. And I also look for this hyphenation pattern, and if I find that, I will remove the start of that substring, because there could be something at the end that is interesting, and then I say that now the exception starts. So the exception should be at the end of the file here. And then I have the patterns. I just remove that specific pattern. And then if it's an exception, I also look at if the line contains a comment, then I will remove that comment, or remove take the things that are before the comment, and then I will split that up into words. So if they actually are multi-line words, and I run handle words here on that line, and then I write the new word out. And handle words, we just split them out into words. And in the case of this specific, then I know that a new word should start with a dot and it should end in a dot. So for these exceptions, I add dot at the beginning and the end. And if the character is a dash in the word, so I go through each character, and if it's a dash, I put a 9 in the word, so it actually says that here I can split it up with a very high certainty. And if it's not, then I put an 8 in there and say, but high frequency here, I don't want you to be split up for this specific example. So, and I don't do that if the things ends in a 9, of course, or if it ends in a dot, because then it's at the beginning of the word or at the end, and it also have a precedence of the number 9 already, so then I don't want this 8. And then I put in the character. So what we end up with then is this dictionary, where we have something up top, some kind of header, and then we just have the patterns here. And at the end of these patterns, I have these kind of patterns. So here we have associate, where we have AS with an 8 between, 9, so, 9, C8. So it actually says exactly the same thing as these patterns, these exception patterns, but we add the logic of the normal patterns here. So we only look for the full word, we only look for exactly these kind of breaks. So I think that should work pretty similar as the other one. And in order to know that I actually have a good working test, I have an old implementation already that uses these kind of dictionaries, and I wanted to use that as a test case. So I've created a bunch of tests here. So I take some hard word here, hyphenation, literally, ironic, regardless, whom, kernel, nonplussed, disinterested, enormity, lieutenant, unabashed, between, Beowulf, and academic. Those are kind of hard words. And I also had a sentence here that I can see that it actually handles sentences as well, because I added that functionality. So in order to run this, I just create a new simple hyphenator here with the English language, and then I just hyphenate over that. The English language is looked up in the property file here. So it's just a bunch of properties and then the dictionary it should use. So nothing really special there. So if we go into the actual code here, we want to read in some stuff. First off, I want to have a map with the hyphenated words and the actual mask, these numbers, that is connected to that hyphenated word. So that is what I want to read in first. And then I want to know the maximum length of a word in my map, so I don't look for words that couldn't be there. If I get words that are really long, then I couldn't even find them up there. And then we have the left and right hyphen min. So that is these kind of end pieces. And then if I hyphenate a word, then I don't want to hyphenate it again, so I have a hyphenation cache here. If we look at the load sequence here, it's pretty much just reading in this resource bundle and then looking at the path of the dictionaries and try to load that specific table. If we look at the load table function, it's also pretty straightforward. A buffered reader, read each line, skip all comments, read in these specific extra things that could be there. UTF-8 is not interesting. And also there could, in this format, which is actually a format that is used by Hunspell, could be compound left hyphen min as well. So just remove those if we see any of those. Or if it's an empty line, remove them as well. Otherwise, if we see a left hyphen min or a right hyphen min, read those in. And down here we have this functionality to find the simple word, which is just a word without the numbers. And then we also want to find the mask with all the numbers here. So we put that in here so we get the mask out. And the simple word, very simple. It's just a way of finding everything that is not a number. Or everything that is a number we replace with nothing. So we get that back. And the mask is pretty much go through each of these, and if we find a number, then we will add that to the specific mask. So we create a mask that is one character longer than the actual simple word, and then we go through each character and see if we find a number there. Then we parse that and put that into the mask. Every other number that is not found will just be 0 because we create a mask with 0 values in them. We could, of course, run a function to actually zero them, but I don't do that in this. I expect them to be 0. So that is how we load the table. Now that we hyphenate words, we have a couple of different functions that we do. So first off, we look and see that we have words that are smaller than, in this case, 4, because then we can't really hyphenate them, so just return the word. We will never do anything with them anyway. And then we take the word, we add these dots at the beginning and the end, so we have the different pieces, and then we will find all the masked pieces. So we will go through all the rules that we have and find the different pieces that we can put together, and then we will merge those pieces into a full mask here, and then we will take that full mask and remove the left -min and right -min values and put those to 0 if we ever get anything at the end or at the beginning of the word. And then we will add the hyphens with this full mask into the word, so we get these kind of soft hyphens. So they are not visible if the words doesn't need to be hyphenated, but they are there. And then we just remove the dots at the beginning and the end of the word and return it. So let's look at the find mask pieces here. That's the first thing that we want to do. Yeah, we can look at the hyphenate here where we go through the word as well. So we have this word pattern here. Everything that is multiple characters of uppercase and lowercase letters is our word pattern. So we go here and find word patterns in the phrase. And if we find any of those, then we will append anything that is before that word. We will look at in the cache. If we don't have a cache hit, then we will hyphenate that word and put that into the cache, and then append that specific value from the cache. And then we will set the position to the end of this found value. And after all these find, we will also add the rest of the phrase if we have anything that is a dot or something like that at the end of the sentence. So that's a way to split up the sentence. Finding these masks pieces is also very small function here. We have all pieces up here. If we find the whole word inside of our array, then we will add that piece in here, because then we have a full word that we can use as the hyphenation target. But we will also find all the different smaller pieces down here. So first off, we will go through and say how long pieces we want. So we start with a piece length of 1, and we go all the way to either the word length or the max word length in our setup up there. So we will get all the pieces with the length of 1, the length of 2, the length of 3, and so on. So this is the iteration through the word, the position of the word. So we go to the word length minus the length of what we actually want to cut out. So this word length. And then we will get the word piece. It's just the word substring of that position plus the word length. So we get a piece of word here. We look in our hyphenated word if we have a piece of that. And then we will create this mask piece here. So this up here is at index 1. This is at index position. And we put that piece in here, the actual array that we find. And the mask piece, very simple this as well. It has an index and a mask. So we can save those here. And the merge that we have to do down here is just putting in the full mask here. And then we go through the actual mask that we have up here. And we will put that into the full mask at the index plus the actual value. So, and we also want to look, so the full mask value that we have here is larger the mask value, then we will keep that. Otherwise, we'll put in the mask value. So that's the way to merge all the pieces in, so we will get the highest value possible for each piece at each position. So then we have pretty much found all the pieces and merged them together. So now we have a full mask of values. The only thing we need to do now is put in the soft hyphens. And this is done with this add hyphens value here. We take the word here. We will create new words that we can put things into. We will go through each character of this word. We'll look at the mask. If the actual mask value is odd here, we'll add a soft hyphen to the word, and then we will add the character of the word and just iterate over that and return this new word. So this algorithm is not the most performant, but I would say that this is the simplest algorithm that I could think of to use this format in order to hyphenate a bunch of words or a full sentence of words. It's not really the best algorithm, but it's not the worst. So I actually looked at the original algorithm. It was using a tree structure, it was using a bunch of different lists and so on, and it had some inspiration from Lisp, the language Lisp, but it was implemented in Java and so on. So it was very complicated and very hard to actually figure out what was wrong with it. And I think it's much more interesting to have code that is well structured and follows the actual language. So if we write something in Java, it should use the language of Java in order to do that task and should be readable. If you use a different language and just merge it over or copy some code over, it's very hard to follow for someone that is attuned to reading Java code. And I also believe that having a functionality that is easy to understand, easy to read, easy to follow, it's much better for debugging and finding actual issues with it. So this was what I wanted to cover today. I hope that you found this interesting. I hope that you learned something today. If you liked this video, give it a like, share it with your friends and colleagues. If you're interested in the code, I will put them up on the GitHub repository that you can find in the descriptions. If you have any comments or suggestions, leave them down in the comment section down below. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.